Alright, so today we're going to be doing 9-3 notes, which is going to be standard scores, also known as z-scores. So in order to do this lesson, you need to make sure you have a standard normal cumulative probability table. It should be in the back of your packet. If you do not have one of these, you can Google it and one will come up. It's like a common generic statistics thing. Okay. So, the standard score, more commonly referred to as the z-score, is a very useful statistic because it allows us to calculate the probability of a score occurring with our normal distribution. It also enables us to compare two scores that are from different normal distributions. So if you're taking something from one bell curve, you can apply it to, you can compare it to another. It basically standardizes all of the measurements. Okay. A standard distribution takes a normal distribution, and it basically converts our mean to 0, converts our standard deviation to 1, and converts all of the corresponding data values into z-scores. How you calculate the z-score, or the z-value rather, is by doing data value minus the mean divided by the standard deviation. So this is your standard normal distribution, which we learned about in 9-2. We have the mean, and then we have one standard deviation from the mean, 2, and so on. And we subtract and add the standard deviation. Now, the standard distribution converts things a little bit differently. Converts it from 0, 1, 2, 3 to negative 1, negative 2, negative 3 on the other side. So we'll convert whatever your score is over here into a standard distribution score. And we'll talk about how this applies, and we'll do an example that shows this. So, given a normal distribution with a mean of 48 and a standard deviation of 5, convert an x value of 40 to a z value and indicate where the z value would be on the standard normal distribution. So I'm going to zoom in here so we can get a better look at this. So the first thing we're going to use is that formula that we just talked about on the previous slide. So that's what I'm using here, just to give you an idea. So this is going to be z is equal to your x value, which they give you of 45, minus your mean, divided by your standard deviation, which is 5. Now, if you do this math, you're going to end up with negative 0.6. Now, the first thing I want to do is I want to set up this curve like we would on 9-2, where we set it up with the mean in the middle, and then calculating each value outward using the standard deviation. So that puts me at 48, and then it puts me at 53, 58, 63, and then going the other way, 43, 38, and 33. So that's what it would look like from our 9-2 notes if we're just doing a normal distribution table. So the one in the purple is the normal. Now I'm going to use green, and I'm going to put the standard values in. Okay. So the way I just put them in different colors so you can see the difference. So standard is always the same. That's why they call it standard. It's 0, 1, 2, 3, negative 1, negative 2, negative 3. So the first thing we're going to do is we're going to find where the value of 45 would have fallen on this curve. So where would 45 have fallen on the purple one? Yeah, like right about here, right? Between between 43 and 48, right? Now let's talk about where this value would have fallen on the green one. Where would it have fallen if we're looking at the green values?
Wait, can you repeat the question? It would be way far. Yeah, can you repeat what you
Yes,
said?
I'll repeat this. So I just put, does everybody understand what I did with the purple one? I put a line where 45 would be because that was my x value. Now we just calculated our z-score, and this corresponds with the green chart. Where would that have fallen? Negative 0.6. Like at the same spot, right? So that's what it does. It converts it to another basically set of parameters. Okay? So it converts it, but it still falls in the same position, right? And it would still be right here. So that's kind of the idea I was trying to show you with the chart, is how it falls in the same spot. So that's the conversion, and that's what happens. So does anybody have any questions about that? Bless you.
So like, when you're doing this, do you have to like relate standard and normal?
No, typically not. Most of the time we're not even going to deal with the normal. I'm just trying to explain to you like why we use this concept. So this one is more of a conceptual question to help you understand the connection between the two. I can take any normal distribution curve and convert it to a standard curve, which standard is more like a universal way, where you can compare multiple curves because they all have the same, parameters. They all have the same scale. Does that make sense?
Mm-hmm.
Okay. All right. So let's move on to the next, because all normal curves all have different scales because they have different standard deviations. So boys' heights in 7th grade are normally distributed with a mean of 62 inches and a standard deviation of 3.2 inches. Determine the z-scores to the nearest hundredth for each of the following heights. So basically here they gave you x. This is x in your formula. So we're just going to calculate each of these. So it's going to be z is equal to, it's always your x value minus your mean divided by your standard deviation. And this comes out to be negative 1.56.
Wait, so where do you get the right now?
You see it?
Yep.
Okay. So yeah, it's just a plugging type of plug in and get the answer situation.
So how would we figure out what it? Okay, never mind.
It's just the formula from the first page, the z-score. We're just using that formula for the x values they gave us. So here they changed the x value to 66 minus my mean divided by my standard deviation.
Oh, okay. No, I didn't fully read before. So never mind.
That's all right. This is 1.25. And then lastly, it's going to be 70 minus 62 divided by 3.2, which comes out to be 2.5. So that's just calculating the z-scores using the formula, converting. This is a conversion. That's what this formula does. All right, is everybody good with the conversion so far? All right, let's move on to the next one. Jeremiah took a standardized test where the mean score, so this is our mean, mu, was 560. The standard deviation was 45. If Jeremiah's score resulted in a z-value of 1.84, what was Jeremiah's score to the nearest whole number? So let's look at the formula. Z equals x minus mean divided by standard deviation. That's the general formula. So we're going to talk about what we have in this formula. So, do we have the z value?
Yes.
What is it?
1.84.
Good. Do we have the x value, his score?
No.
We do have his score, don't we?
No.
Oh, we don't have his score. Just kidding. I don't know why I said that. So do we have the mean?
Yes.
Yes, we do. And do we have the standard deviation? Sorry, I was like... Okay, so we're going to plug in what we have to find what we want to know. So that's going to be 1.84 equals x minus the mean over the standard deviation, which is 45. And then we can just use algebra to solve this. So I'm going to put it over 1, and I'm going to cross multiply. And that's going to come out to be x minus 560 is equal to whatever 1.4 times 45 is, or 1.84 times 45, 82.8. And then what will be my last step to solve for x? Good. We add the 560 to both sides, and we get x equals 642.8, which is approximately 6.43 because they told me to round to the nearest whole number. So the idea is they can give you any of those 3 values and ask you to find the 4th one. It doesn't always have to be the z-score you're going to be calculating. Does that make sense? So you have the tools, from taking algebra to know how to solve for any of these, really. So yeah. So is everybody good with 1, 2, and 3? All right, we're going to move on to how to read this chart now. So, have your chart out and ready. We're going to talk about it. So, reading a normal distribution table. Z-scores have probabilities that can be found in a normal distribution table. See page 15, that's the one I asked you to rip out. This table allows you to quickly determine the cumulative probability of any z-score from negative 3.49 to 3.49. In the partial table above, we can see the z-score of 0.72 has a probability of 0.7642 or 76.42%. This corresponds to the percentage of data that falls at or below a certain observation. This is known as a percentile. So, here's how you read the chart, and I feel like once I say this, it makes a lot more sense. So, this column right here, the vertical column, is the tenths place. Okay, it deals with the tenths place. So, if you have like 1.7, 0.7, this column is the hundredths place. So, if we're looking at the z-score of 0.72, our tenths place is 0.7, and our hundredths place is 0.02. So does everybody see why we chose that value to pick? So you look at the tenths place, then you look at the hundredths place. So across is the hundredths, this is the tenths. So you do the 0.7 and then you move over to what it's
that makes sense.
Do you guys see it? Because I feel like it's one of those things that like it just takes you to understand what we're doing, and then what?
What is it for this? Like reading normal 0.
Yeah, you have to read the chart and it converts it into a probability.
Oh, okay.
Yep. All right.
What chart is this?
The one I asked you to rip out, which is the one you're looking at right now.
Yeah.
So, let's practice reading it.
Oh,
You got it?
yeah, I found it.
State the probability associated with each z-score. So, what do you notice about this one? Does it have a hundredths place? No. No, so its hundredths place is an implied what?
0.
Very good. Very good. So, just keep that in mind when you use the chart. You're going to have a hundredths place, and if it doesn't have one, you're just going to go to the 0 row. So, I'm going to go to my chart, and it's going to be the one on the left of the two, because the left one's negative, the right one's positive. You're going to go down to negative 1.7, and how many am I going to go over?
1.
Just 1, and that's going to give me 0.0446, also known as 4.46%. So does everybody see that on their chart? Good. Just want to make sure. Now we're going to do the same procedure for this one. We're going to go to negative 0.9 on the chart, and we're going to go over all the way to what?
0.8.
0.8, yeah, 0.08, which gives us 0.1635, also known as 16.35%. So these are the probabilities associated with each z-score. So how this basically works and what the purpose is, if we have one of those standard distribution curves, okay, you know how on the normal distribution curve we were adding up the percentages to find the probability of each thing happening? This is doing that same procedure for the standard distribution curve. So where it falls, it's like what percentage of the data falls before it, to the left of it. That's what this is calculating. So the next one is going to be 0. So I go to 0.0, which is actually on both charts, the negative and the positive. So you can either use the one on the left or the right. And what are you getting when you go to 0.0? Good. 0.5, also known as 50%. 50%. You got to go 2 decimal points. No, it doesn't matter zeros after it. If a 0 is here, you always move the decimal 2 places to the right when you're going from decimal to percent. And the next one This one you're going to have to use the one on the right, which is the positives. So you go to 2.3, and then you go over to 0.02, and you should get 0.9898, also known as 98.98%. So I do want to talk a little bit about the first number C. I know we have two number C's. Z-score of 0 is 50%. Anybody have a prediction on why that is, now that we've seen what the standard distribution bell curve looks like?
Just like the negative numbers, like if you look at the chart, like at the top for like negative 3.4, it's like almost starting at like 0, so it's kind of like in between. And then like 3.4 on the positive side is almost like up to like a whole.
Exactly. So if we look at this table over here, like this one, see how 0 is the exact middle of it? Which means that 50% of the data is to the left of it, right? So everything you calculate with this table calculates the probability to the left of it. So you're going to learn about why that's important. We have to know it's to the left. And sometimes we have to adjust the fact that it's always to the left and do some algebra to adjust that if we don't want the probability on the left. So let's go ahead and talk about percentile. So it's the same procedure. You're going to find negative 2.8. So I go to my table and I look for negative 2.8, and what's that value? 0.0188. I'm getting 0.0026. Did you
look at the one right above?
You look at the, is it negative?
Yeah, it's negative, that's why. It's negative 2.8. And remember, it doesn't have a hundreds place, so it's 0 in the column. Do you see it?
No.
Negative 2.8. Right here.
Oh, you don't do the 2 and then.
No, because it's still in the tens place. Only when you go to the hundreds place do you use this. Exactly. Yep. Only if it has a second decimal portion. And how we actually say this is we convert it to a percent, and this is a tiny 0.26, but instead of saying the percent symbol, you just say percentile. That's literally the only difference with percentile, okay? So instead of putting the percent symbol, you just say percentile.
What difference does it make?
It's just depending on what kind of question they're asking. So they may say what percentile are they in, you just have to word it correctly. But no, the actual math is the exact same. So the next one here, 1.7, and then go over to 0.02. And you should get 0.9573. Everybody see where that comes from? Convert this to a percentage. And this is in the percentile. And now we're going to state the percent of data that is above a certain z-score. So we're going to talk about how we have to adjust this. So I want to talk about this for a second. You don't have to write this. If you're dealing with a normal distribution curve, okay, or standard distribution curve, say you calculate the probability at 0. What you're calculating is this area right here, the area to the left of whatever value you're looking at. But the problem here is this is always below when we do the calculation. But they want above. So does anybody have an idea on how we could find above if the calculations are always below?
Subtract that of 1.
Yes, subtract from 1. So the whole thing adds up to, the whole thing's out of 1. Probability is always out of 1, right? So you're going to do 1 minus the z-score you received, which will give you above. So we look at our z-score as we've been doing. You're going to calculate it from the chart, okay? So negative 0.5 and then go over to 6.6. And you should get, when you do this calculation, 0.2877. And now to adjust for the fact that we want above, we do 1 minus this value, which ultimately comes out to be 71.23% once you convert it to a percentage. Excuse me. So does everybody see how I got that?
For that, like, are you just finding, like, the number, like, the percent of the numbers that are, like, bigger,
Yeah, exactly. So like if this falls on the chart somewhere around here, right? And you're finding this instead of to the left.
Okay.
Yep. Alright, so for the next one, it's 1.18. Now if you use the chart, you should get 0.8810. So you have to do 1 minus that value. And that will come out to be 11.9%. So 11.9% of the data is above 1.18. How does everybody feel about this? Alright, so now that we've talked about a few conversions, we're going to do some problems that involve these concepts. So, finding probabilities with z-scores. So the main idea here is finding the z-score alone isn't always enough because it only calculates the probability to the left of that score. Sometimes you got to find probabilities between two scores, everything before and then after a certain score, okay? And then sometimes you're also going to have to find probabilities to the right of the score, which is what we just did. So you have to learn how to manipulate the z-score when necessary. So this is the one we've been doing for a while. When you want to find the probability that data falls to the left of the score, you would just find the z-score itself, because that's the thing that the z-score does. So let me just read through the blurb here. When working with z-scores, you will encounter one of 4 situations. Use a normal distribution table. Will allow you to find probabilities based on the z-score. Understand the probability in the table is cumulative probability, meaning the probability represents the area percentage to the left of the z-score. So if that's not what they want, you have to adjust it. So in this case it says, bottles of apple juice have weights that are normally distributed with a mean of 64 ounces and a standard deviation of 4 ounces. What percentage of bottles would be expected to have less than 58 ounces? So we have to use our formula. Z is equal to the amount we're given, x, minus our mean, divided by our standard deviation. And when you do this math, you should get negative 1.5. Now, you're going to take the probability of that. So that's the probability that x is less than 58. And to do this math, you're going to look at the z-score chart, okay, the chart. So you're going to look at negative 1.5. And when you do that, you should get 0.0668, also known as 6.68%. So I want to show you what this would look like on the table. So with a standard distribution curve, this right here is 0. This is negative 1. And this here is negative 2. So negative 1.5 falls somewhere between negative 1 and negative 2, right? So it's all of this. This is what we just calculated right here. Okay. Everything to the left of that. 6.68% of the data is to the left of that. How does everybody feel about example 7? Okay. The daily high temperatures in July are normally distributed with a mean of 84 degrees Fahrenheit and a standard deviation of 4 degrees Fahrenheit. What percentage of the 31 days of July can a person expect to have temperatures above 90 degrees? So here they want above. So the first thing we're going to do is calculate our z value, z-score. So this is the value x we're given, 90 minus the mean, divided by our standard deviation. And when you do this math, you end up with 1.5. So remember, 1.5 is going to be, if this is 0, this is 1, and this is 2, 1.5 is going to be somewhere around here, right? And we want to find all of this that comes after it, above it, right? Instead of below it. So in order to do this, the first thing we need to do is we need to find, because we're trying to find the probability that x is greater than 90, above 90. So that's going to be equal to 1 minus whatever the chart tells us for 1.5. Because remember, if it's above, you have to do 1 minus the value. And that comes out to be 0.9332. And if you do the math, this comes out to be 6.68%. So 6.68% of the data is above 1.5 or 90 degrees. Now, does anybody have a prediction on why the values came out to be the same for 7 and 8?
I was literally gonna ask.
It's like the same chunk of the graph.
Exactly. It's the same size chunk of the graph, right?
Yeah.
So over here, it's the same size chunk as this graph. It's just in a different spot. It's actually a mirror of it, right? So it represents the same size proportion of the graph, but we're talking about different pieces of data. So for example, I can take 50% of the graph on the lower, 50% on the upper. It will take up the same space on the graph, but represent a different section of it. So that's the reason they came out to be the same. And as you can see how the z-scores were the same but different signs, which is also an indicator. Any questions about 7 or 8, above and below? Everybody feel good about above and below? All right. So now we're going to move on to a few more complex situations between and outside. Luckily, there's a formula for this, so it's not too hard to figure out. So the probability, data falls between two z-scores, all right? So we got z1 and z2. So how we calculate this is we find the probability of z2 minus the probability of z1. So what's important about this method is you have to make sure you're taking the one on the right minus the one on the left. So the one that's larger, take away larger minus smaller. Okay, very important. Otherwise, it's going to come out to be the wrong sign. Because like if you do this one minus this one, it's not giving you the right information. So the weight of Siamese cats are normally distributed with a mean of 64 pounds and a standard deviation of 8.8 pounds. What percentage of cats would be expected to have weights between? So when you're doing these type of problems with the between or the outside, you have to do two calculations. So I have to calculate this as x and this is x. I'm going to have two separate calculations. So that's going to be z is equal to 5.2 and then minus my mean divided by my standard deviation. And this comes out to be negative 1.5. And then I'm going to do another calculation for this one. Z is equal to 7.6 minus my mean divided by my standard deviation. And this one comes out to be 1.2. So you do those two calculations. Now what I like to do at this stage is draw a little bit of a sketch of this. So negative 1.5 is somewhere around here, right? And 1.2 is like around here. So my goal is to find this probability in the middle, right? So in order to do this, we have to first find the, use the chart to find the probability of each of those happening. So you're going to use the chart for each of those values. And when I use the chart for the negative 1.5, I get 0.0668. And when I use the chart for this one, I get 0.8849. Now the rule is I have to do the one on the right minus the one on the left. So which one's going to come first?
The one on the right.
Good, which is 0.8849. Does everybody see why this one has to come first? It's to the right on the bell curve, minus the one on the left. So that's why I think drawing a sketch kind of helps. And this comes out to be 81.81%. So 81.81% of the data falls between these two. Sorry. My recycling bin is in the way always. So does anybody have any questions about that one? Everybody understand the order of subtraction here? Because subtraction is not a commutative property, so you have to be careful with it. So the next one. The scores on a math test were normally distributed with a mean of 75 points and a standard deviation of 6. What percentage of the students scored lower than 65 points, or higher than 90. So, once again, these are both x values. So we have to do two separate calculations here, okay? So this situation is scored lower than this or higher than this. So it's excluding the middle, actually. So let's calculate our z-scores, and we'll talk about what that means. So z is equal to x minus our mean divided by our standard deviation and that comes out to be, I'll do it down below because it's running out of room, 2.5. And the other one I'll do in purple. Z is equal to 65 minus 75 divided by 6, which comes out to be negative. This is a negative. It doesn't look that obvious. Hang on, I'll redraw it. Negative 1.67. So right now I just found the z values. Now I need to convert them with the chart. So I'm going to convert each of those values. So this one converts to 0.9938. And this one converts to 0.0475. So I have their conversions. Now I want to use the table to talk about what this represents. So, negative 1.67 falls about right here, right? And 2.5 falls somewhere over here. Now, it's asking us students who scored lower or higher. So I'm talking about the students who scored lower than this value or higher than this value. What one is this one excluding? What information is this excluding?
The people in the middle.
Everything in the middle. We don't care about anybody who scored between the two. We just want to know lower and higher. We want to know the highs and the lows.
Yeah.
So the way we do this math, they actually give us a nice little formula for this. 1 plus p of z1 minus p of z2. So it's going to be 1 plus, remember, p of z1 is the one on the left. So the one on the left, which is this one right here, minus the one on the right, which is this one. And we always use the chart value to do this. And when you do the math here, this comes out to be 5.37%. So a small amount. Remember, the tails of the bell curve are the smallest representation portion. So yeah, that's the main idea. We have one more question to go over, and it just kind of combines everything. So does anybody have any questions about this one in particular? Everybody understand what the placement? I think the placement is one of the hardest parts here. You really just look at, I always like to draw it out because it's visual. So the weights of 100 chow dogs are normally distributed with a mean of 50 pounds and a standard deviation of 3 pounds. Estimate the number of dogs whose weight was, so we're basically just doing 4 different calculations here. So weight was less than 45 pounds. So these are all your x values. So it's going to be z equals 45 minus your mean divided by your standard deviation, which comes out to be z of 45 minus 50 divided by 3, approximately negative 1.67. So we use our chart to find that value, and it's going to come out to be 4.75%. So why on this one did I just have to use the table and that was it? Anybody know why I didn't have to do any other calculations here? Less than. So whenever it's less than, we're just looking at everything to the left. So that one's simple. So the next one we'll do this one first. C is actually easier. So for C, we're going to do the same thing. We're going to do our calculation. Z is equal to 57 minus 50 over 3. And that gives me Z equals whatever 7 divided by 3 is. 2.33. And if we do that calculation, now the problem is this comes out to be 0.0475. But on this one, it's more than 57. So how do I adjust here? Yep, 1 minus the value, which comes out to be 95.25%. So remember, if it's more than, you have to take your chart value 1 minus the chart. Everybody feel okay about that? And now we're going to do between the two. So this is where you can work smarter and not harder. Haven't we already calculated the Z value for both of those? So we don't have to do it again. But if it's between, we just have to follow the rules, right? It's going to be the one that's larger minus the one that's smaller. So it's going to be whatever this one came out to be, 2.33. So between 45 and this, so it's going to be the 57 one first. So if we go to 2.33 on my chart. Yep. 0.9901. Wait, was that? That wasn't it. I'm trying to read it with one hand, so I can't like use my finger. Oh, I was right. Okay. Sorry. Minus the smaller one, which is going to be, so 45 came out to be negative 1.67. So I'm getting 0.0475, which is equal to 94.26%. And then that should be the answer, yeah. And then the next one wants to know outside of the two. So for this one, we do 1 plus, it's going to be the first one minus the second one. So in this case, this one is the second one. This one is the first one. So it's going to be 1 plus 0.475 minus 0.9901 is equal to 5.74%. So we're just using basically all the concepts we use in the first problems. And I just used the math I already did, the z-scores I already found from the previous parts, because they still use the same numbers. So it's just making sure you follow the formulas, that's really it. So any questions?